In this video, we'll be looking at applications of probability distributions. So after the completion of this topic, we'll be done looking at all new notes for Math 145. There will just be a computer lab to do to support your learning in statistics and probability. Okay, so we'll be performing calculations involving applications of probabilities, standard normal distributions, and the normal distribution. Okay, so question number 1, we have a survey of types of cybersecurity attacks for a corporate business in 1 month, and it shows the following breakdown: that there are 64 phishing attacks, 43 SQL attacks, and 21 malware attacks. From a random draw, what is the probability that the type of attack is a phishing attack in the 1 month span? So we want to know, what is the probability of X equaling phishing? We know that we have 64 phishing attacks within that 1 month out of a total of, so we have 64, 43, 21, 128 attacks in total that are examined. And there is 0.5 probability, which is 50% probability of it being a phishing attack. Part B, from a random draw, what is the probability that the type of attack will not be a phishing attack in that 1 month span? So probability that X is not phishing. So we have 64 that are phishing. So we have 43 that are SQL, 21 that are malware out of our 128 in total, which again is 64 over 128 or 0.5. Another way you can look at this is that the probability of it not being phishing is equal to, if you take all possible cases, so 100%, and take out the ones that are phishing, you get 1 minus 0.5, and that has a 50% probability again. Okay, in part C, we're asked, from the random draw, what is the probability that the type of attack, this should be a K, is a malware attack in the 1 month span? So P of X equaling malware. And there's 21 attacks that are malware to be expected out of the 128. So 0.1641, 16.41% chance of occurring. Okay. And question number 2, it's a multiple choice problem. It says, which of the following values cannot be probabilities? So recall, possible values for probability range between 0 and 1. Okay, so probabilities cannot be negative, which means that we can already identify that number 2 is not possible, and they cannot be greater than 1. So number 5 and number 6, are both greater than 1. So there are 3 different cases that cannot be values for probabilities. The rest of them are acceptable. Question number 3. The life of a computer disk drive is normally distributed with a mean of 3,500 hours and a standard deviation of 75 hours. We want to know between which 2 hours are approximately 68% of the disks last for. So using our empirical rule, we know that 68% of the data lies within 1 standard deviation of the mean. So I'm going to actually write that out. According to the empirical rule, 68% of the data lies within 1 standard deviation of the mean. Okay, so looking at this visually, we have our normal distribution. We know that we have the mean, x bar, and 68% will be within x bar minus s and x bar plus s. Okay, so that's 68% in this whole green thing, green area. Okay, so what we want to know is what are the values for 1 standard deviation for the mean. We know that x bar is equal to 3,500 hours and the standard deviation s is 75 hours. So x bar plus or minus 1s is equal to 3,500 plus or minus 75. And both of these have units of hours. Okay. This will give us an upper and lower limit. The lower limit is when you subtract 75 from 3,500 hours, and the upper limit comes from adding it. So you get 3,575 hours. So we can identify the upper and lower ranges for the middle 68% above in the question. In question 2, it's saying out of 10,000 discs, approximately how many will last between 3,350 hours and 3,650 hours. So if we draw this, we can choose to use the empirical rule here, or we can calculate the relevant Z values. We know the mean is 3,500 and the lower value is 3,350 and the upper value is 3,650, which happens to be 2 standard deviations from the mean. So this works out to be, we want to know what is the probability of x being between 3,350 and 3,650. It doesn't say that we have to use the empirical rule, so we could actually use our z-scores, so calculate the relevant z values, calculate the probabilities using your table, and we know that the probability of being within 2 standard deviations of the mean is 0.95. That's using the empirical rule. Okay, but we were actually asked how many out of the 10,000 discs would be expected to be within that range. So we're actually looking for the expected value, and that's equal to n times p. We have 10,000 discs, and we expect that 95% of them are within that range. So we get 9,500 discs. Question number 4, it says, cybercrimes can do serious harm to an organization's bottom line. A recent study found that the median annualized cost of cybercrime for 50 organizations in their study was $5.9 million per year. The companies in the study experienced an average of 72 successful attacks per week with a standard deviation of 4.3. According to the empirical rule, 68% of the attacks should fall into which interval? And we want to determine the lower and upper limits of the middle 68%. So we know that our mean is 72 attacks, and our standard deviation is 4.3 attacks. So we want the middle 68% using the empirical rule. %, or 0.68 as an area under the curve, and that will be within 1 standard deviation of the mean. Okay, so we can actually write those endpoints as x bar plus s and x bar minus s. So we're looking for the lower and upper values. So according to the empirical rule, %, of the values fall within 1 standard deviation of your mean. Okay, so we want x bar plus or minus 1 standard deviation, so 73 plus or minus 4.3 attacks, which gives us a lower bound of 67.7 and an upper bound of 76.3. Okay, so that answers our question. So the 60% of the attacks would lie between 67.7 attacks per week and 76.3 attacks per week. Question 5 says, consider the usable lifetime of all of D-cell alkaline batteries sold by We Have Power Incorporated in a year. So as part of their quality assurance program, the company has conducted tests on battery life. For their D-cell batteries, the mean life is 20 hours. And then it says the useful life of battery follows a normal distribution with a standard deviation of 2 hours. Okay, so we know that the mean is 20 hours and the standard deviation is 2 hours. And the battery life follows a normal distribution. Based on the empirical rule and using the mean and the standard deviation provided, compute the upper and lower boundaries of where we can expect 68%, 95%, and 99.7% of the data to be located around the mean. And draw the normal curve and label the standard deviation, the mean standard deviation values and boundaries below. Okay, so using the empirical rule, we can identify all of those things, but first I like to think of this in terms of my diagram, and we can write things out. So we know that we have our mean, which is 20, and we know almost all the data, so 99.7% of the data falls within 3 standard deviations of the mean. So this is x bar minus 3s and x bar plus 3s. So we know that 99.7% of values fall within 3 standard deviations of the mean. And so that's x bar plus or minus 3s, which is 20 plus or minus 3 times 2, and gives us a lower value of 14 hours and an upper value of 26 hours. So we can fill that in. So 14 and 26. Okay, we're going to end up with 3 equal sections here. So you can use your imagination that everything is perfectly equal. We have x bar plus 1 standard deviation, x bar plus 2 standard deviations, and then in the opposite direction we have minus 1 standard deviation and minus 2 standard deviations. And the relevant values will be 18 and 22, and we will also have 16 up to 24. It's filling out the rest of this. So according to the empirical rule, we know that 68% of values fall within 1 standard deviation of the mean, which is x bar plus or minus 1s, 20 plus or minus 1 times 2, which is up from 18 up to 22 hours, which I've already identified in red. And the middle part of the empirical rule, which is 95% of the values, fall within 2 standard deviations of the mean, which is x bar plus or minus 2 times s, 20 plus or minus 2 times 2, which is 16 up to 24 hours. That's identified in purple. So you can find any other particular values using your z-score table and identifying the probabilities using the table as well. Okay, so in the next part of the problem, we're still going to use the empirical rule. So what percentage of batteries will last between 16 and 24 hours? Looking right at our initial table in part A, we know that it will be 95%. So P, probability that lasts between 16 and 24 hours, 0.95. Since we have 20, 16, and 24, these are both within 2 standard deviations of the mean. And so this whole area is 0.95 using the imperial rule. Okay, for part C, what percentage of batteries will last more than 22 hours? So there's a key part of the question there, and it's more than. So we have 22 hours, and we want the area to the right of it. We know that the area, everything to the left is 0.5. Everything between 20 and 22 hours is 68% divided by 2, which is 34%. And so the probability that X is greater than 22 hours is equal to 0.5 minus 0.34, which is equal to 0.16. I should add, it's asking for the percentage, so this is actually 16%, and the previous question would have been 95%. In part D, what percentage will last less than 24 hours? So make a sketch. We know that 24 is 2 standard deviations. Less than 24 means everything to the left. So the area between 20 and 24 is 0.95 divided by 2, 0.475. And everything to the left of the mean is 1/2. So the probability that x is less than 24 hours is equal to 0.5 plus 0.475, which is 0.975 or 97.5%. Part E says, how many standard deviations from the mean does a value x of 18 fall? We know that 18 is equal to 20 minus 1 standard deviation. So 20 minus 2. So 18 hours is exactly 1 standard deviation to the left of the mean. And then part F, what percentage of batteries will fall between 20 and 24 hours? We draw a sketch. So we have 20, 24 hours, which has 2 standard deviations between those two values. We know that 95% of data fall within 2 standard deviations of the mean, but this is only looking at half of that. So 0.95 divided by 2, which is 0.475. So the probability that x lies between 20 hours and 24 hours is equal to 0.475 or 47.5%. Okay. And in the last couple questions, we have, so given data below, it gives the average load time for a sample of 10 web pages. We want to calculate the probability the web page loads in less than 1 second based on this data. And then in part B, we're going to do something else. So first thing you need to do is use your calculator to calculate the mean and the sample standard deviation. Okay, you're going to want to make sure you pause your calculator, try doing this on your own, and compare your answers. There is a difference between calculating the sample standard deviation and the population standard deviation, so make sure you calculate the sample standard deviation here. And what we want is a probability that selecting a website at random, it will load in less than 1 second. Okay, we're told, well, we're not told actually, so we are going to assume it follows a normal distribution. Okay, so in order to compare it to standard or normal distribution, we need to figure out what it is when we standardize the data, and we want to calculate the z-score. So 1 minus the mean divided by s is, I should say, instead of putting x here, it should be x minus x bar, which is 1 minus x bar, which is 2.51. And I'm actually going to leave my variable s here. So I don't want you to round this value. Avoid rounding the standard deviation. You can use the value right from your calculator's memory. And when we type that in, you're going to get negative 0.295927, which rounds to negative 0.30. We round z to 2 decimal places because your table is always the 2 decimal places. So we want the probability that z is less than negative 0.30. So we have our mean of 0, negative 0.30, and we want the area to the left of that. What our table is able to tell us is the area between 0 and 0.3 is 0.1179. So the desired area is 1 minus 0.1179, and that is equal to 0.3821. So the probability that your web page will load in less than 1 second based on that data is 38.21%. In part B, it says remove the outlier from the data and recalculate the probability that the website loads in less than 1 second. So based on what we previously looked at, 38% chance that it would load in that time. And you can see that looking at the data, there's one value that stands out as an outlier, 17 seconds. Everything else is within a much more reasonable amount of time. So what we're going to do here is remove outlier, value of 17 seconds. So you should actually grab your calculator now, type in all the data again, make sure you do not type in 17 seconds, and you'll find that the mean is 0.9 seconds, and the standard deviation is 0.360555128, and we want to recalculate the probability that it loads in less than 1 second. So we recalculate our z-score. We find that it's equal to 0.277350098, which rounds to 0.28, 2 decimal places. And we are looking at what is the probability of z being less than 0.28. So it's everything to the left of 0.28. Okay, everything to the left of 0 is 0.5, and everything to the between 0 and 0.28 is 0.1103. So our calculated probability is 0.5 plus 0.1103 for a total of 0.6103. So with that one outlier data point removed, we can say that it's likely that 61.03% of web pages would load in less than 1 second. So we want to compare our answers from part A and part B, and what do you notice? And we can say, so when the outlier is removed, the probability of any web page loading in less than 1 second increases dramatically. And that's as its mean drops to below 1 second. Okay, so you can see here how it's really important to have an accurate collection of data, and it may be even more helpful to look at a sample of more than simply 10 web pages to accurately make an estimation about how likely it would be for a website to load in less than 1 second. Okay, so that's the end of the Unit 4 notes. Please give all the D12 quizzes, so homework quiz number 12 and 13 a try, and let me know if you have any questions.